Good morning, lads and ladies. Welcome back to Calc 1. Today is an exciting day because today we are going to introduce the notation, which will be the bane of your existence for not just the remainder of this class, but probably also the first half of Calc 2. If you learn to love the symbol that we're going to meet today, then you've got a career as a mathematician or an engineer or something else. And if you don't learn to love this thing, then maybe not. And then that might sound like high pressure, but the truth is that that was the same with the derivative. I just didn't say it. The derivative is hugely important, and we introduced it gently. This thing is also hugely important, but we're going to introduce it slightly less gently because at this point you guys have matured a little bit as mathematics students. The full importance of this thing won't become clear for a while, and it's going to seem a little bit intimidating at first. And I know we've been going through a handful of things that have intimidating notation, so I'm going to do my best to show you this thing in a way that explains its meaning and helps you get a little bit comfortable with it before you have to get in and do the nitty-gritty work with it. So with that little intro out of the way, let's do it. We got to launch this. The object in question, you can probably guess if you've leafed forwards in the book and seen that the calc books later pages are mostly full of these elongated, scary looking S's. Or if you've ever seen a movie with a mathematical subplot, surely you've seen these things spinning around in the background in that scene where the main character is thinking really, really hard. Yeah, Adrian, I can talk after class, sure. So this, of course, is MAC2311, section 002. It is a lecture. And today is the 22nd. Today, we're going to introduce the integral. So like I've been saying, calculus is sort of split into two worlds, right? There's differential calculus, which is what we've been doing, and there's integral calculus, which is what we are about to move into. And today we are going to learn finally exactly what an integral is. This is section 5.2. Also, before I get into it, a little announcement. I do think at this point, everybody who needed to take the makeup test has taken it, so I can finally go ahead and grade and publish your exam. So your exam 2 grades, they'll be in by this evening. Probably by around 10 p.m. All right. So I know a lot of us are nervous about exam 2. I've gone through most of your tests, and most of them look pretty good. I'm actually quite proud of the way you guys performed. But I've held off on releasing anything because I still had 1 or 2 people that needed to take a makeup exam as late as yesterday, so I want to hold off on that. But they'll be out. They'll be out today. Don't stress. So, is there any other bookkeeping stuff we need to worry about? Oh, there is. There's one other thing. We're approaching the withdrawal date for this class, so let me pull up a copy of your syllabus here. Here we are. So the last day to withdraw from this class, that is the last day to get a W on your transcript instead of an A through F letter grade, is the 24th, 2 days from today, which will be Wednesday. So if you're kind of on the fence about whether or not you want to stay in the class, if you're having a hard time deciding, Wednesday is the day to make that decision by. Here's the standard advice. Basic advice is this. If exams 1 and 2 are both greater than 70%, you should stay. If exams 1 and 2 are both like less than 70%, you should probably consider the drop. There's some leeway here. You could replace 70% with 60%. It kind of depends on what your goals for the class are. If you're in a position where you need a C or better in the class, which I think is the case for most people, then I would use 70% as the cutoff here because that's the obvious thing to do. That's the cutoff for a C. If one exam is greater than 70% and the other is less than 70%, then you should come talk to me. So I used to use 60% as the cutoff. I would say, if exams 1 and 2 were both greater than 60%, both passing scores, then stay in the class. If they're both below 60%, both failing scores, then you should consider dropping. And if one is greater than 60 and the other one is less than 60, then you should come talk to me. But I know that most of you, a 65 or whatever in the class, a D in the class is not sufficient to move on. So I'm adjusting this slightly. But really, this is just basic guideline stuff. It's not meant to be followed rigorously. But if you're just genuinely not sure what to do, these are the sort of fundamental guidelines that I like to offer. So if neither exam has gone well enough for you that you will be happy with that grade as your final grade, then it's probably wise to consider letting go of this class for the semester. If both exams are strong enough that you're happy with those, the average of those 2 grades being your final grade, then certainly you should stay. That's an indication you're on a great track. And if one is greater than your target goal and another one is less than your target goal, then you should really come have a chat with me in office hours and talk about kind of how things are going, what the trend is like. This is not hard and fast. I have certainly had people whose first 2 exams were below 70% and still went on to earn strong grades in the class. And I've had people who nailed exams 1 and 2 managed to not pass the class. Those things can happen also, but it's quite rare. Both of those exceptions are quite rare. So this is a reasonable framework with which to get started on your decision. And if you're having a hard time, regardless of the category you fall into, please come talk to me in office hours. I'm happy to talk with you guys about grades. We can do so in private. We can come up with a personal strategy. And there are some things I can do to help kind of loosen the deadlines a little bit if necessary. But I just wanted to make you aware that 3/24, this Wednesday, is the deadline to withdraw. And generally, if you've done well on the first 2 exams, you can expect to do well in the class. If you've not done well on the first 2 exams, it's going to be difficult to do well in the class. And kind of intuitive stuff, but just make sure it's in your brain because, yeah, this Wednesday is the deadline. All right. So let's do it. Section 5.2.
Professor?
Yes.
What do you consider well in context to the, if you did well on the first 2 exams, then you should keep going?
I would say whatever your target score is for the class. So there are things like the study guides and like the homework that have the ability to boost your grade a little bit, right? All of the study guides together are amount to about the strength, about the weight of an exam. But because the final is weighted heavier, I usually would say that the best way to get a feel for where you are in the class is to just look at your exam average. So if your exam average is below the target goal you need for this class, like if you need a C or better to move on to the next class, then I would say if your exam average is below a 70%, then that means you should at least consider letting go of the course. And if your exam average is above a 70%, then you should probably stay in because you're on track to get your goal. But it really depends on what your goal is. If you're okay, if your academic plan allows you to earn something less than a 70% in this class and still continue with what you're trying to do, then this number will be different. But I would say the threshold for what most people need is 70% because most people need a C to go on in the next class. So I would consider doing well on one of these tests being a 70% or greater, and the test not going especially well being a grade less than 70%.
Okay, thank you.
Right, but that varies for different people. It really does. If you had something horrible going on around the time of exam one, you know, your house burned down or something like that, then getting a 60% on exam one is probably not indicative of your skills, and you shouldn't take it too hard. But yeah, 70% is the usual threshold because most people need a C or better to move on to the next class. All right. So the definite integral. Where to begin? There's so much good stuff. So last section, in section 5.1, we learned that the area, I should say the exact area under the graph of the positive function f of x is lim n to infinity of Rn, which is lim n to infinity of sigma I from 1 to n f of xi times delta x. So this was kind of the big discovery and the big tool that we cooked up in the last section. If you want to find the exact area under the graph of f of x, as long as that function is above the x-axis everywhere, then you can calculate this limit, and that will give you the exact area. Now remember, this object right here is what we call Rn. It's the right endpoint Riemann sum. You could use the left endpoint Riemann sum too, but everybody uses this one because it's easier to work with. This thing has a special name. And under certain contexts, it can be understood as the area bounded by the graph f of x and the x-axis. That thing is called the definite integral. The signed area, I should say, bounded by f of x and the x-axis from x equals a to x equals b is called the definite integral of f of x from a to b, denoted by this thing. So I'm going to explain what I mean by signed area, but it's the same thing that you were thinking about before, right? You're finding the area bounded by the graph and the x-axis between two x values, a and b. The symbol we use for that is this big, long, curly S. All right, this symbol right here is an S. It's just stretched out. And it stands for the word sum, S-U-M, in the same way that capital sigma stands for the word sum. It's just that this sum is a continuous one. And it is defined to be, so this equal sign with a colon on the left means is defined to be equal to the limit as n goes to infinity of sigma I from 1 to n f of xi times delta x. And sort of each object in the Riemann sum on the right has a corresponding object on the left. The f of xi here are your heights or y values, and those are the same as the f of x's in here. The delta x here are sort of like your widths or little changes in x. That's represented here by the differential dx. The sort of fundamental idea is that as n goes to infinity, delta x gets really, really small, right? As you use more and more and more rectangles, the width of each rectangle gets smaller and smaller. So as n goes to infinity, delta x becomes this infinitely small little change in x, which is precisely what we've denoted by dx in the past. So as delta x gets really, 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 really small, we call it a dx. And we no longer have sample points xi in here. Instead of specific finite number of points xi, we just have x inside of f here. And what this means is really we're trying to sum all of these heights times these tiny little infinitesimal widths over all of the numbers between a and b. Instead of taking a finite number of sample points, remember, between any two real numbers, there's infinitely many other real numbers. So kind of the way mathematicians think about this thing is as a continuous sum. But for us right now, as we're getting used to it, we're going to think of it as the signed area. And I want to explain to you what I mean by signed area. But I'll give you a second to look at this. I'm going to flip over to the textbook and make sure I'm not skipping over anything before we move on to the explanation of what we mean by signed area. Yeah, we'll need to talk about integrability, but I think first it's better to, yeah. No, that's a little too much for you. But yeah, okay, signed area and then integrability. There's a question in chat. The two dots mean by definition, right? So this equal sign says that, you know, this thing is equal to this thing. And the two dots mean I'm defining the object on the left. So this object, which is the new object, the thing we haven't fucked with in the past, is by definition equal to this limit. Fair question. Yeah, this notation means by definition is equal to. All right. So what do we mean by signed area? If you think about your Riemann sums, those heights came from y values on the graph. And in all the examples we did in class and all the examples we looked at in the homework, the function was always above the x-axis. Those y values were always positive. But we'd like to generalize and be able to handle functions that aren't always positive. And then we need to see how that affects the situation we're discussing now with the definite integral. So what do we mean by signed area? I mean, area that's measured with a sign is either positive or negative, depending on whether that area is associated with a part of the graph or the function is positive or negative. So let me sketch here for you. Let's do something like this. Over here, I'll call this A, and over here, I'll call this little b. This is the graph of the function f of x. And what we've been doing lately is finding the area bounded by the graph f of x from A to B. The thing is, here, some of this area lives above the x-axis and some of it lives below the x-axis. And all the examples we've seen so far, all the area lived above the x-axis. Let me go ahead and call this first chunk here A1 for the first area. I'll call this chunk here A2 for the second area. And I'll call this chunk over here A3 for the third area, right? Because each one of these is kind of their own isolated region. What the integral here is going to return, so by signed area, what we mean is that the integral from a to b of f of x dx, this is the object that we just said is supposed to measure the area. It's equal to the limit of the Riemann sum, measuring the area bounded by the purple curve from A over here to B over here, so it should measure all of these areas, is going to measure the two guys who are above the x-axis as positive, but the guy who's below the x-axis as negative. This would be A1 minus A2 plus A3. So the A2 region here, which sits below the x-axis, is measured with a negative sign, precisely because it sits below the x-axis. If you were to look at any y value down here, right, like imagine the little Riemann rectangle that goes right here. The height there is going to be negative in the Riemann sum, right? Like maybe this y value right here is like -2. That means in your Riemann sum, the little f of xi, maybe it's like, you know, x7 or something over here. This is like your seventh rectangle. You've got 1, 2, 3, 4, 5, 6, 7. This guy is going to have a negative, right? The y value here, f of x7, would be negative because the graph is below the x-axis. And the same is true for all of the little rectangles in here. They would all have negative heights. So this whole chunk, A2, is going to end up being measured as a negative area. The subtle thing here that you need to be careful of is that a question can ask you, find the area bounded versus finding the integral. If I asked you to find the integral, which is this thing, this is correct. If I asked you to find the total area bounded, you would need to fix this piece and make it positive. And it's a little bit subtle. So area beneath the x-axis, or I should say the horizontal axis, will be measured as negative by the definite integral. And that's what we mean by signed area. Is this making sense? Are there any questions about this? Yeah, I see there's something in chat here. Yeah, we can talk through this just one more time real quick. So remember, this thing, by definition, is the limit of the Riemann sum, right? Lim n to infinity, sum I from 1 to n, f of xi times delta x. What it returns is something we call the signed area bounded by f of x and the x-axis. What we mean by signed area is that if area is above the x-axis, we consider it as positive. So this guy and this guy would contribute positive area. And area that's beneath the x-axis, like this guy, is measured by the integral as being negative. So if you were to compute this integral through any means, you were to use a calculator, you were to do it by hand using the methods I'm going to teach you later, or by using the limit of the Riemann sum, if you were to compute this integral by any means, it will return to you positive A1, positive A3, and negative A2, all added up. The A2 is negative because this region lies beneath the horizontal axis, which means all the y values along the curve here are negative. So all the little rectangles' heights would be considered negative. Since all those little heights are negative, all of this area is going to be considered negative. It's a little bit counterintuitive, but that's what we mean by signed area. If the graph was completely underneath the x-axis, then all of the area would be considered negative. We would still have area. It would just be all negative. If the graph is completely above the x-axis, then all the area would be positive. If the graph is completely beneath the x-axis, all the area would be negative. And if there's a mix and mash of both, then the area that's beneath the x-axis is negative, and the area that's above the x-axis is positive. All right. Before we can get into calculation, there's one other thing I need to talk about, and that's integrability, which is a fancy word meaning for what functions does integral a to b f of x dx exist, right? Or when can I integrate a function? This means integrability is like, can we integrate this function, this or that function? It's the integral version of differentiability. So remember, way back when we introduced the derivative, we had to talk about whether a function was differentiable or not, right? Not every function has a derivative at every point. The absolute value function, remember, is not differentiable at that pointy part. It turns out integrability is much softer. Most functions are integrable. So here's the result. As long as f of x has finitely many discontinuities and no infinite discontinuities, and I mean different things by this, no infinite discontinuities, then f of x is integrable. So it can't be discontinuous at infinitely many places, and it can't have a discontinuity where it blows up to infinity. So what does that mean? For example, this function is just fine, even though it has a jump discontinuity here. So here, the integral from 0 to 2, we'll call this f of x, of f of x dx, that would just be the area under the graph from x equals 0 over here to x equals 2. This is fine. The area here, this is a rectangular region, so we can say right away what the exact area here is, right? The base here is 2, the height here is 1, and so the total area here, the area bounded by f of x from 0 to 2, which is this thing, would just be 2. If I were to stop here at 3, that's okay also, even though I'm jumping over this discontinuity. Remember, if a function was discontinuous, then you couldn't differentiate it. That was a big deal. But here, even though this thing is discontinuous, we can still integrate it. The discontinuity doesn't mess things up for the integral. So what would be the integral from 0 to 3, from over here all the way to over here? Well, it would be equal to 2, which is this. But then there's also this down here. This would be measured as having area 2. This would be measured as having area -1. So this would be measured as having integral from 0 to 3 equal to 1. And the jump discontinuity here doesn't hurt. It's okay. I can still say very clearly what the area bounded here is. There's a little bit of a question about what happens right at this point. All right, so think of what we have up here. Area that's above the x-axis is measured as positive. Area that's beneath the x-axis is measured as negative. Here's some area above the x-axis. Here's some area beneath the x-axis. The area of this region, this has length 1, going from 2 to 3, and the height here is like -1, right? Or you could say that the total area down here is 1, and it's beneath the x-axis. So it would be measured as negative. So this is 2 plus -1, 2 minus 1, which is 1. Well, I'm choosing to look at the integral from 0 to 3. So I'm looking at all of this area. I'm looking at everything from 0 all the way up to 3, which means I'm looking at this stuff plus this stuff. This stuff is positive. This stuff is negative. Is this settling in? Are we getting comfy with this? Let's look at what the integral from 2 to 4 would be. So if I just wanted to look at the signed area bounded by f of x from x equals 2 to x equals 4, that's this region down here. Its length is 2, and the height here is like -1. You could say that the area of this region is 2, but it's all underneath the x-axis. So this would be -2. I'm doing my best to be a little bit redundant here. So the big idea is just that area above the x-axis is measured as positive, and area that's beneath the x-axis is measured as negative. If you calculate the area of this chunk, it's a rectangle. Its length is 2, its height is 1. So this area right here is 2 times 1, which is 2. Since it's all above the x-axis, we count it as positive. So the integral from 0 to 2 of f of x dx, which is the signed area under f of x from x equals 0 to x equals 2, would be exactly this area, which is 2. The integral from 0 to 3 of f of x dx, that means I want to find all the area bounded by f of x and the x-axis from x equals 0 over here to x equals 3 right here. That means I'm looking for all the area enclosed here. Part of that is above the x-axis. That's this piece, which we just said a second ago was 2. Part of that is beneath the x-axis, the piece from 2 to 3. This area is 1, but it's beneath the x-axis, so it gets measured as negative. So this first piece is giving us the 2 that you see right here. This piece is giving us the -1 that you see right here. And when you add those up, you get 1. So I would say that the signed area under f of x from 0 to 3 is 1, because you've got 2 positive and 1 negative. And then down here at the bottom, we have the integral from 2 to 4. So that means I'm looking for all the area over here, all the area bounded by f of x and the x-axis from 2 to 4. So from this x value to this x value. Again, we have a rectangle, right? What's the area of this rectangle? Well, its width is 2 and its height is 1. So the area here is 2, but it's all underneath the x-axis. So it all gets measured as negative. So the integral from 2 to 4 of f of x dx is -2. The area here is 2. Sorry, the area here is 2, but it's all underneath the x-axis. So we would say that the integral is -2. Who can help me out bringing it all the way home here? What's the integral from 0 to 4 of f of x dx?
0.
Very good. Yeah, you guys nailed it. This is 0. I would think of this as 2 plus -2, which is indeed 0. You remember the little story I told at the end of class last week about going to the grocery store and going back home, and how the velocity integral comes out to the distance, but only if the velocity function is negative? This is what's going on there. Here's me walking to the grocery store at a constant speed, maybe 1 mile an hour. Here's me walking back from the grocery store at a constant speed of 1 mile an hour. So I'm walking in one direction, my velocity is positive. Walking in the other direction, my velocity is negative. So the integral, which would tell me my total displacement, would be 0, because I finished back where I started. But the total distance I covered would be the total area. Right, so this difference between area and signed area, that's what I mean. I'll talk a lot more about the velocity stuff a little bit down the road, but I just wanted to prime you for that idea. The reason I'm using this particular example here is because it has a discontinuity. And I'll say again, remember, if a function is discontinuous at x equals a, it's automatically not differentiable there. You cannot differentiate a function at a point where it is discontinuous. But the discontinuity doesn't fuck up the area thing at all. That's really cool. It's actually really surprising. So the fact that there's this jump discontinuity here doesn't upset the integral operator the same way it upsets the differential operator. If you asked me to differentiate this function, I wouldn't be able to tell you what the derivative is at 2. But it doesn't have any effect on the area thing, because there's still 2 very clear pieces of area here. Kind of the take-home lesson from that is that what happens at one point doesn't affect the integral at all. One point contributes no area because it has no width. A point is infinitely narrow. So the fact that there's a little jump discontinuity here does not upset the integral. And that's what I'm talking about when I say integrability. So this function, even with its discontinuity, is still integrable. It still has an integral. We can still integrate it. But how can you fuck this up? How can we make a function that isn't integrable? Or what would a function that's not integrable look like? There's 2 examples that I'd like to show you really quick, and then we'll move on from this, and it won't have much of a bearing on our later discussions. But if you ever take a graduate mathematics class or a mathematics class that looks carefully at integrability, you'll see that this is quite a big deal. So can we integrate f of x equals 1 over x squared from x equals -1 to x equals 1? In other words, and this is how you might see it phrased on a question, is f of x equals 1 over x squared integrable on the interval -1 to 1. And it will be helpful here to look at the graph. Here's the graph of 1 over x squared. It has a vertical asymptote at x equals 0. It has horizontal asymptotes out here. Those aren't really consequential. 0 is here. -1 is here. This is the point -1, 1. 1 is here. This is the point 1, 1. So what I would be asking for is the signed area bounded by this function all the way through here. So kind of this area.
Would the shaded in part not go all the way through because of the asymptote?
I think you're onto something there. Can you be a little bit more specific? With the shaded part,
Like it can't go through the vertical asymptote, like we can't,
very
can
good.
we combine it all together?
So the vertical asymptote is the problem. You've identified the problem correctly. The vertical asymptote at x equals 0 is what kind of discontinuity? Do you guys remember back when we were talking about how to classify discontinuities in section 2.5? What kind of discontinuity does this function have at 0? Is it a removable discontinuity? Is it a jump discontinuity? Is it a different kind?
Discontinuity.
Say it one more time.
Infinite discontinuity.
Excellent. Yeah, it's an infinite discontinuity. The vertical asymptote at x equals 0 is an infinite discontinuity. And if you look at the definition of integrable on the previous page, it said that f is integrable as long as it has finitely many discontinuities and none of those discontinuities are infinite. This is an infinite discontinuity. So no, f of x is not integrable. It's not integrable, integrable on -1 to 1 because x equals 0 is in -1 to 1 and f of x has an infinite discontinuity there. What's more, f of x here, f of x equals 1 over x squared is not integrable on any interval containing 0. So like, if you asked me the same question, but replaced the left endpoint here with 0, the answer would still be no. If you had any interval here that contains the number 0, this function is not integrable on that interval. The problem is the infinite height, right? The truth is that no matter how I draw this, I'm not going to be able to capture it all because this height goes up and up and up and up and up forever, right? Like this. There's a vertical asymptote there. The height goes all the way up to infinity. The function blows up at x equals 0. So it's going to be very hard to talk about the area there. And yeah, it means that we can't solve the integral from -1 to 1 of f of x equals 1 over x squared until you get to 7.8 in Calc 2. I'll show you how to do this one there. There is a workaround. It's complicated. It involves careful work with limits, but it is possible under the right, situations if you use the right tools. But in terms of Riemann integrability, the Riemann integral from -1 to 1 of this function does not exist. Yeah, so you cannot find this area using a Riemann integral. You have to introduce new tools called improper integrals. Another example that we've seen, and it's a little bit more exotic, and that's, I'm afraid, necessary in order to come up with one, is I'll just ask it in the formal way first, is the Dirichlet function. And we talked about this guy early on. D of x is equal to 1 if x is rational, and 0 if x is irrational. Is this integrable? Let's say on the interval, you could use any interval, but let's say interval 0 to 2. Dirichlet, D-I-R-I-C-H-L-E-T. I left off the L. Yeah, Dirichlet. So this was a function that we looked at back when we were first starting to talk about differentiability and integrability. Its graph, I put 1 up here, looks like this. If I feed this thing 1 as an input, 1 is a rational number. If I feed it 1/2 as an input, 1/2 is a rational number. If I feed it 1/3 or 1/4 or 1/5, all of those are rational numbers. So there's lots of points up here. In fact, there's infinitely many points up here on any interval, because between any two real numbers, there's infinitely many rational numbers. So the graph of this function, remember, is like a fine sprinkling of dust along the line y equals 1. But it's not a solid line. So here, I'll give some examples. D of 0 equals 1. D of 1 equals 1. D of 1/2 equals 1. D of 1/4 equals 1. D of 7/9 equals 1. D of any fraction is equal to 1. Any whole number or fraction. However, D of the square root of 2 is 0. D of pi is 0. D of root 2/2 is 0. D of any irrational is 0, like D of E is 0. This is a fairly exotic function. It's weird, right? It's very weird. The question I want to answer is it integrable? So the question I need to answer is, does this have any infinite discontinuities? Yes or no? And does this have a finite amount of discontinuities on the interval 0 to 2? If the answer to both of those questions is yes, I should say it this way. If it has no infinite discontinuities and it has only a finite number of discontinuities on the interval 0 to 2, then this function would be integrable. Is this function integrable? Remember, so down here at e and pi, there's actually a lot of stuff down here. Every irrational number, like 1 over the square root of 2 is like right here. Square root of 2 itself is like right here. So we've definitely got a point down here, and we've got lots of other points down here. Every irrational number, there is a point down here. In fact, the sprinkling of dust is much thicker down here. So this is sort of what the graph of the Dirichlet function looks like. You've got a faint sprinkling of dust up there along the line y equals 1, and you've got a much thicker sprinkling of dust down here along the line y equals 0. What do we think? Is this function integrable from 0 to 2? Can I talk about the area bounded by this function from 0 to 2 in any reasonable way?
Wouldn't this, because between two real numbers, there's an infinite amount of numbers in between, and here we've shown that there's going to be more irrational numbers on the function, that it's infinitely discontinuous, because it hops back and forth between the two so often you can't.
Very good. Very, very good. Yes. Both of you and Trevor are correct. This function is not integrable. D of x is not integrable on the interval 0 to 2 because it has, because d of x has infinitely many discontinuities. On 0 to 2. In fact, we said exactly where this function is continuous and exactly where it is discontinuous. It's discontinuous everywhere. D of x is discontinuous, meaning not continuous, discontinuous at all real numbers. Right? It jumps back and forth infinitely many times between any two real numbers. That was exactly the observation we needed. D of x jumps from 0 to 1 infinitely many times on any interval, because between any two rational numbers, take your favorite two rational numbers like 1/2 and 1. Those are both rational numbers. They can both be written as fractions using whole numbers. Between those two rational numbers, there are infinitely many rationals and infinitely many irrationals. Between any two numbers, between any two real numbers, there are infinitely many rationals and infinitely many irrationals. So every time the input goes from rational to irrational, this function has a jump discontinuity. It jumps from 0 to 1 anytime the input goes from rational or irrational to rational. And it jumps from 1 back to 0 anytime the input goes from rational back to irrational. because between any two numbers, there are infinitely many irrationals and infinitely many rationals. This function is not integrable on any interval. Fascinating stuff. So here's the idea. At every rational number up here, you have a very, very thin spike. I'm going to try to get this across. Between at any rational number, say here at 1, there's going to be a point up here, right? Here's the point 1, 1. So if you try to think about the area here, there is a very, very, very thin, infinitely thin spike right here at 1. But then right next to it, there's a portion where the function is equal to 0. So there's no area there. But then right next to that, there's another infinitely thin little spike. So this function is discontinuous everywhere, which means that there's no piece that has a width, right? There is no like solid stretch up here. There is no place where this graph up here is solid. If you wanted to try and picture the area, I don't encourage you to draw what I'm about to draw, but if you try to picture the area, yeah, it would look like dropping down from each point up here is an infinitely thin little line. But lines have area 0 because their width is 0. So sort of if you want to try and think of the area, it'll confuse things because it'll look like it's shaded in if you drew this, but it's not really shaded in. Each one of these little vertical lines is infinitely narrow. It contributes no area. And between each of those lines, there's infinitely many points down here where the y value is 0. So you never get a solid chunk, which means you never get any area. Now it turns out that both of these functions, there are ways we can answer the question using more sophisticated integration techniques. Like for this guy, we use what's called the Lebesgue integral. For this guy, we use what's called an improper Riemann integral. Here, if you use the Lebesgue integral, you'll find that the integral over any interval is 0 because there's way more shit down here than there is up here. It really is like a very faint sprinkling of dust here and a basically solid line down here. There's that many more irrational numbers than there are rational numbers. This is a relatively new thing. Mathematicians didn't discover this until the 1920s. Don't feel bad if it's weird. The area up here on the 1 over x squared graph turns out to be infinite. But there are functions that look like this that still have finite area. So it's very complicated. But the big thing I want you guys to take away from this is that neither of these functions are integrable in the Riemann integral sense, in the sense that we are talking about. The Dirichlet function is not integrable because it has infinitely many discontinuities. And 1 over x squared is not integrable because it has one infinite discontinuity. And if you have either of those things, any infinite discontinuities, which are, remember, vertical asymptotes, any vertical asymptotes, any infinite discontinuities, automatically you're not integrable. And then down here, if you have infinitely many discontinuities, no matter how big the jump, it doesn't matter. If there's infinitely many of them, automatically you're not integrable. Those are the big things. The good news is, unlike differentiability, where I'm going to ask you questions, is this differentiable or isn't this? I'm not really going to ask you this shit on a test. You just need to know it. It's an important concept. And there might be some concept-focused true-false questions that probe at this, but it's not the sort of thing where you're going to get in and do a calculation and show me that the function is or is not integrable. So you just need to remember the definition. Right? Definitions are hugely important. Remember, a function is integrable if it has finitely many discontinuities and no infinite discontinuities. So you can have jumps like this. You can have 2, 3, 4, 5, 10, a million jumps like this, as long as it's finitely many. And you can have discontinuities of all sorts of flavors, but you cannot have an infinite discontinuity. You cannot have a discontinuity where the function blows up to infinity. Is this landing? Are we feeling comfortable with this idea? The basic thing is you have to be able to talk about an area. If the height blows up to infinity, then it's very hard to talk about the area, because what the fuck, how much area is there here, right? From here all the way up to the vertical, the infinity up here, how much area is that? It's very, very hard to say, because you can't be like width times height, because height is infinite there. That's a problem. Similarly, down here, how much area is there? Well, it's very hard to say because there's no width. So here, there's no measurable height. And here, there's no measurable width. As long as you stay away from those two problems, you're good. If your function is continuous, you're good. If your function is piecewise continuous, meaning it only has finitely many little jump discontinuities, you're good. As long as you don't do any weird shit like this or weird shit like this, your function is integrable. So with that in hand, let's do some integrals. I think I have a black pen and I want to switch to black here if I can. So here, no. Damn it. Fuck. Hold on. All right. I lied, I don't have a black pen. We're going to stick with purple. So let's do some integrals. Right. Here is the illustration kind of explaining why area beneath the x-axis is measured as negative. All of these rectangles have like a negative height. So when we actually look at the exact area, that area will be measured as negative. Here is our theorem. If you're continuous, or if you only have a finite number of jump discontinuities, then your function is integrable, can be integrated. And of course, the definition, right? The exact area, the integral from a to b of f of x dx is the limit of the Riemann sum, where delta x is what you think it is, and xi is what you think it is. So let's take this guy. Let's express lim n to infinity, sigma I from 1 to n, xi cubed plus the sine of xi all times delta x as a definite integral. So this is really just about matching up the pieces. Remember what I said about like this being like the dx and these xi's being like the x's and this sigma as being like the integral symbol? You just got to match up the pieces. Now, did they give me something? Did they specify? Yeah, okay, on the interval 0 to pi. There are ways to solve these problems where they don't specify an interval, but they would need to tell you a little bit more about what delta x is or what xi's are. What is my function here? Which part of this whole expression tells me what the function f of x is? Yeah, everything to the right of the sigma. Well, not everything to the right of the sigma. So here's everything to the right of the sigma, but before the delta x. Remember delta x, this is like the dx.
Wouldn't it be like x cubed plus sine x?
Exactly.
Or I mean xi?
Yeah. No, that's it exactly. So f of x here is, well, let me say it like this. F of xi is the thing inside there. That's xi cubed plus the sine of xi. So f of x is x cubed plus the sine of x. And of course, the delta x becomes dx. So the expression given is equal to the integral of f of x, which is x cubed plus the sine of x dx. And then they told me what my interval is. The integral is going from 0 to pi. That's it. That's the whole thing. Now, soon I will tell you how to solve this integral. Right now, we don't know how. But the problem didn't ask us to solve it. It just asked to say, write this as an integral. And you should make sure you're comfy with where each piece came from. Remember that the thing inside here this piece is f of xi. That's how our formula for the Riemann sum works, right? It's sigma I from 1 to n, f of xi times delta x. So this thing is your function with x replaced by xi. So your function must just be x cubed plus sine x. In other words, this thing tells you the area under this function from x equals 0 to x equals pi. And again, computing this is tricky. We're not going to worry about computing it right now. We're just worrying about understanding the notation. Are there any questions about where this came from? Well, it comes from the definition. All right, remember down here, the integral from a to b of f of x dx is equal to the limit as n goes to infinity, sigma I from 1 to n, f of xi times delta x. So we just really, the only thing we had to figure out here is our function. What is f? Compare the pieces. All right, I'll try to line them up here. Look at this. Lim n to infinity, lim n to infinity. Sigma I from 1 to n, sigma I from 1 to n. The next thing in here is f of xi. So this thing has to be f of xi. Well, what is the function that's being applied to xi in here? You have xi cubed and the sine of xi. So this is really about understanding function notation at this point. I'm just asking what function, when you plug in xi for x, gives you this? And the answer is clearly x cubed plus sine x, because what we have there is xi cubed plus sine of xi. All right. Let's try another one. They had something there slightly different. So evaluating integrals, right? These are the rules for the sigma operator that we covered last week. Remember these? You can split up sigma over addition or subtraction. You can pop out constants. And then you have these summation formulas. So here they want us to set up this thing as an integral and then evaluate the integral using the definition. This is going to take a minute. So let me see, is there anything else that I want to cover today before we jump to that? That will eat up the rest of the class time for sure. Yeah, let me look at this first. We've done some of those evaluating Riemann sums things. Let's look at these. Evaluate the integral from 0 to 1 of the square root of 1 minus x squared dx and integral from 0 to 3 of x plus 1 dx using geometry. So no Riemann sums, no limits. That's the good news here. We're going to use geometry. So you're not going to set up a Riemann sum or evaluate any summation formulas. What you do need to do here is think about the graphs. Let me start with this one. Integral 0 to 3, x plus 1 dx. This is the signed area under f of x equals x plus 1 from x equals 0 to x equals 3. And in this case, we're very lucky because this graph is linear. So let's draw the graph. X plus 1 looks like this. All right, it's a line with slope 1 and y-intercept 1. I'm going to call this out here 3. Kind of forget about this tick mark. All right, so the area I'm trying to find, what that integral does is it measures this area. And I can find this area. This is not terribly hard to do. We can find the area in this case using geometry. I can split this region up. I can kind of think about it as like this region together with this region. One is a triangle and the other one is a rectangle. So the rectangle region, this has area equal to 3 times 1, which is 3. And this region, it's a triangle, so its area is 1/2 times its base, which is 3, times its height. Now, what is the height of this triangle? Well, we're going from here up to here. So I need to know what's the y value here and what's the y value here. The y value here is 1. What is the y value all the way up here? Along the graph y equals x plus 1 at x equals 3.
4.
4, good. So the height of this is 4 minus 1, which is 3. So this would be 9/2. Therefore, the integral from 0 to 3 of x plus 1 dx is equal to the total area in here, which is 3 plus 9/2, which is 6/2 plus 9/2, which is 15/2. This is not usually how we're going to evaluate integrals, but it is a useful trick from time to time. And it is a great way of checking whether you understand what the definite integral does. Questions about how we arrive at 15/2 here? Okay, the next one is a little bit more fun. How do I find the integral from 0 to 1 of the square root of 1 minus x squared dx? I'll tell you that to do this integral sort of the normal way, the way we're going to learn how to do integrals down the road, is tricky. You won't learn it until Calc 2. It's called trig sum. But this is a special one, just like the last one was special, in that we can use geometry. So find this using geometry. And what I mean by that is that if you draw the area, you'll recognize it as something you know how to find the area of using techniques that you learned in middle school. It all boils down to knowing what the graph of this looks like. Let's graph y equals the square root of 1 minus x squared. Who can tell me what this graph looks like? Anybody? I'll show you where we get it from, but first let me just go ahead and graph it for you. Here it is. What is this? Someone has-
Semicircle.
Good, it's a semicircle. The whole circle is this. It's the unit circle. It's a circle of radius 1. Why? Well, if you want to graph this, you can square both sides. If you square the right-hand side, the square and the square root cancel. And then you add the x squared over. And this is the equation of the unit circle. Remember, in general, the equation of a circle with center A comma B and radius R is x minus a squared plus y minus b squared equals r squared. Thus, y equals the square root of 1 minus x squared. If you were to take this with the plus and the minus, you would get the whole semicircle. But since you're just taking the positive square root, you're only getting the positive y values, is the equation of the upper half semicircle. Centered at 0, I should say centered at 0, 0, with radius 1. So that graph is this. All right, -1 over here, -1 comma 0. And over here we have 1 comma 0. So the area this area here is 1/2 the area of the circle. Circle with radius 1. And the area of a circle is pi times the radius squared. So this is pi times 1 squared, like that. 1 squared is 1, so this is 1/2 pi, or pi over 2. Therefore, and I should say the area we're looking for, which is just the area from 0 to 1, square root 1 minus x squared dx, is half of this area, because it's a quarter of the circle, right? Half of this, or 1/4 of the area of the circle, which is pi over 4. So if we were trying to integrate from -1 to 1, that would give you the area of the whole semicircle, which is pi over 2. If you want to integrate just from 0 to 1, that would give you half of that, or 1/4 of the whole circle, which is pi over 4. All right, this is where we have to stop for today. The notation we're introducing, the definite integral, is a big deal. And you guys want to work on this immediately. You want to look at the examples in the book and then begin on the homework. I'm going to go through WebAssign in a minute and clear out all the extension requests from last week. So if you haven't finished that up, please finish that up first. But then there will be a new homework dropping a little bit later today where I'll ask you guys to do precisely these sort of things. There will also be some stuff in there on antiderivatives. And I'll talk with you about that on Wednesday. And then on Friday, we're going to talk about what's called the fundamental theorem of calculus. When you hear the words theorem and fundamental in the same sentence, you know you're in for something big. So please make sure you finished up last week's homework. Make sure you take a look at some of the example problems in the book. And then a little bit later today, get started on that homework. Look at least 1 or 2 of those problems before class on Wednesday, and you'll be in good shape. Any questions for me before we conclude for the day?
Yes. So I don't know if you've read my email yet, but I'm fine meeting while my parents are there. I just what time would work best for you?
Oh, let me turn off my screen share here. Give me just 1 second. Oh, that's right. I do remember. Yeah. We spoke. If you want to come by today's office hour, 1 to 2 p.m. works fine for me.
Okay, I can't make the office hours. I have a class at that time.
I see. Okay. What times work for you then?
I am free anytime after 2:30 today. Anytime Tuesday in the afternoon. I'd like to meet with you before Wednesday.
Let's shoot for, let me take a look at your email. I'll reply to that, but I think probably, oh, let's see, Tuesday. No, I'm going to get vaccinated. Let's do today at 2:30 then.
Okay.
All right. I'll send a Zoom link to your email.
Okay. Thank you.
All right.
Okay.
Take care, guys.